All right, so this video right here is explaining homework 2 that is on chapter 12. So the first problem, we have a tugboat that pulls, a small barge through a harbor, and it wants us to calculate the time that it's required to increase the speed from initial velocity of 1 meters per second to a final velocity of 2.5 meters per second. The only thing that's given to us is the weight of the tug and barge was 360 kilonewtons, but we're also given the force. I was seeing the solution. They used like a graph to get this, but we already had it, so we didn't have to go through that step. So now to find the time required, we have to get the acceleration first. So force equals mass times acceleration. Get the acceleration by itself. We're given the force, put it right here. And then the mass, we do know what the mass is. Plug it in right over here. But just to make things look neater, I kept the m. And the v, the velocity, well, we could simplify it by we could simplify this whole thing to this, and then we remember that a is equal to dv over dt. Switch places with a and dt, so we could integrate this and get the time. So we integrate this to we ended up getting t, but we're focusing on this right here. We could put m into 127,000 over here, integrate this part right here, and we get this. Solve for this, and this is what we get, and then plug that back into this part right here. Earlier I talked about m. This is how we solve it. We know that the weight is equal to m times gravity times g. Get m by itself, and then right here I converted the original value of 3,600 kilonewtons to newtons, so we could get kilograms. This is what we get. Plug that in over here, plug in what we solved right here over here, and this is the time we get. So 18.84 seconds. Now it wants us to also get the distance traveled during that time interval. So we have to remember this from homework 11. This will help us get the distance. Switch places with a and dx. So we could integrate this and get x, which will be our distance. We also do the same thing as we did earlier, get m and 27,000 out of it just to make it much simpler. And then we focus on integrating this, which gets us this. Solve for that, and this is what we get. And then we're back to so integrating dx, it gets us x, and then integrating this part right here gets us this, and then we have our mass, so just plug all that stuff in, and this is the distance we get, 36.14 meters. All right, in problem 2 we have a truck that's pulling on I think this is a rock, and it has a pallet underneath. Oh, sorry, it's a boulder, and it wants us to find the horizontal force between the tires and the ground, and the force between the boulder and the pallet. All right, so first what we need, before we figure out the tires and the ground, we need to figure out this tension right here. So we start right here. You got a free body diagram right here. What's down is the mass of both the boulder and the pallet times gravity. And then we take the sum of forces in the y direction. This is what we get right here. The sum of forces in the y direction equals the total mass of these two times acceleration. And we get this is what we get right here. Going in the positive direction is these two tensions, negative direction is this. You know, we solve for t, and this gives us our tension. So now that we have that, we could draw a free body diagram of the truck. And then we take some forces in the x direction, which gives us our horizontal force, which will be 764.60. Now it also wants us to find the force between the boulder and the pallet. So here's a free body diagram of the boulder. So we have some forces going down. It's the mass of the boulder times gravity, and some forces going up, which is the force between the boulder and the pallet. So take the sum of forces in the y direction, which is equal the mass of the boulder times the acceleration of the boulder. We take these into account, which is right here. Get the force by itself, plug in the values. We also have to remember that the mass is equal to the weight over gravity, which we did here. And this what gets us our force. And these are final answers. Okay, so for problem 3, we're given this figure right here. Wants us to find the angle of the cord and also the tension of the cord. So to find the angle, you know, we take the free body diagram of the ball, and then, you know, the angle's right here, but we would draw the straight line. It'll be opposite of it, so that's why we have the angle right here. Take the sum of forces in the x direction, which will equal to mass times acceleration. Here's a sum of the force. Sorry, this is in the y direction. We focus on the x one first. So the sum of forces in the x direction is just the tension, the sine of the tension, and also acceleration can also, word up here, can also equal to velocity squared over rho, and rho is really just the distance from here to here. It's 1.8 sine theta, and then here we take the sum of forces in the y direction, which is t cosine minus mass times gravity. A way you could have done this is just solve for t on both sides and set it equal to each other, because t is the only thing we don't know. So we know everything else, so it'll be easier to solve that way. The way I did it is here I set t equal to itself and then plugged it in on this part right here. Yeah, that's what I did over here. Simplified it, I got this. Then I remember that sine squared plus cosine squared equals 1. So I could substitute sine squared to 1 minus cosine squared. Plug that back in here. And then I could simplify it to cosine squared plus 0.9061 cosine minus 1. And I could use the quadratic formula for this to find cosine data. Plug in the quadratic formula, given these two values, it can be negative, so use this one right here. Then use the inverse cosine to get the angle, which is given right here. Now it wants us to find the tension, so that's pretty easy. We could use this one right here, plug in the values, plug in the cosine that we found on the bottom, and it gives us this. So these are our final answers for problem 3. Problem 4, given this figure right here with a wrecking ball, it wants us to find the tension of top of the C of the swing. So I wrote the free body diagram of this right here, and then I made this like right here, our x direction, just like our y. Oh, sorry, x direction here. And this right here is our y. So as you can see right here, going up is positive. So yeah, the sum of forces in the x direction equals mass times acceleration. So this easily could be t, and then this right here could be minus w cosine 20 degrees. And then, oh right, so the acceleration here is 0. So the answer is simply just going to be, the tension is simply going to be the weight times cosine 20 degrees, is given the weight, which is 130. It's given in the problem statement, and that's what we get for our tension for part A. Part B wants to find the tension of the cable at the bottom D of the swing, where the speed of B is 13.2. So focusing on this right here. Wrote the free body diagram. It's a pretty simple one. There's the sum of forces in the y direction equals mass times acceleration. And then I could simplify this part right here. We know that m is equal to w over gravity. Wrote that in, substitute that for m. A, we talked before, is v squared over rho. Plug that in here. And then get tension by itself. We just add the w to the other side. Plug in the values, and we're given this for our answer. All right, in problem 5, we're given the churn table, and it wants us to find the coefficient of static friction. So I know we could use this equation right here, which is the resultant force equals static frictions times n, and it could be simplified to mass times gravity. I'll talk about that later in the problem, but we need to find the velocity of point B. We could use this equation right here. We know the initial velocity is 0, so just plug in these values, which are given in the problem statement, and this is what we get. So we want to figure out the resultant force. Another way we could find it is getting the forces in this direction and the forces in this direction. This is a free body diagram of like a top view of the churn table. So for this one, going this way, going in the y direction, it would just be the mass of in point B times the acceleration of point B. This one right here is the mass of B, and then the acceleration could be substituted to this again, which is v squared over rho. Rho is this distance right here, and then this shouldn't be squared, sorry, should just be that right there. But then later, to get the resultant force, we do square these two, because the resultant force is really just this squared plus this squared, and then you take the square root of it. I forgot that you could take out m, the mass of in point B, out, and just focus on the accelerations. You know, I added the values that we know, and my final answer is 2.316 times the mass of B, because we don't know what this is yet. And then there's a free body diagram of the churn table, like more of a front view. So we got the weight going down and the natural, or the n going up. Take the sums of it in the y direction. That's what we get, and we get n is equal to w, which is also equal to mass of B times gravity. Now we have n. So for this equation right here, we have n, and we have the resultant force. We could simplify n to this again. So get the friction. So to get the static friction by itself, we divide mb and g to the resultant force, which is shown right here. Remember, we didn't know what mb was, but now it doesn't really matter because we divide it by mb, so it cancels out. So it's just the resultant force over gravity, and that gives us our static friction. All right, so problem 6. So it talks about Venus. We're given the orbital velocity of it. We're also given the mean distance from the center of the sun to the center of Venus, and we're given the radius of the sun. So the first thing it asks us to do is to get the mass of the sun. So we use these equations right here. They're given from the book and also the PowerPoint slides. We can also remember that F could also equal to mass times acceleration. We talked about it before. Acceleration could equal to v squared over radius, or rho, which is, you know, it's essentially radius. Set these two equal to each other. And we could solve for the M, the big M, which is the mass of the sun. And then we know our radius is given to us, but it's in kilometers, so we just convert it to meters. We want everything in meters. Same thing with the velocity is given to us, but converted to meters per second, so it's given to us in kilometers over hour. And then for the big G, this is the universal gravitational constant. I had to look up this value, but it's a constant value, so it's always going to be the same. So, you know, plug in the values in the equation for M, and this is where we're given for our mass of the sun. And then we also want to find the acceleration of gravity at the surface of the sun. So same equation, but this time instead of being mass times acceleration, it's mass times gravity. And then we're using the radius of the sun, which is the big R. So, you know, just set G by itself, divide M, cancels out. So we're left with this right here. We're given the radius of the sun, just again in kilometers. So we had to convert it to meters, kilometers, I mean. Oh, km. Plug it in here, and this is what we're getting for the acceleration of gravity. And problem 7, we're given this figure right here, and we're also given this and this. So it wants us to show that F is inversely proportional to the square of the distance R from the particle to the center of the force O. So, you know, we know this from the textbook or the PowerPoint slides. So we substitute this into wherever there's a U. Things in it 3 times. So do that. And then we can also replace this R with this right here that's given to us. So we're left with this. Now, this is what I was getting confused. So you only get the double derivative of this section right here, not the whole thing right here, just this section. So that's what I did. I could also just get 1 over RO out, 'cause it's a common denominator, so you could pull it out here. So the double derivative of 2 minus cosine is just cosine, and then plus 2 minus cosine. So you know the cosines cancel out, and now we just have to solve for R. So right here we have 2 over RO. You know, set everything to the other side, and this is what we're left with. And this right here, it shows that F is proportional to 1 over R squared, or it's inversely proportional to R squared. That's our final answer. So problem 8, this one's the one that gave me the most trouble. So we're given this figure right here, and it wants us to solve for 3 things. So it wants us to determine the increase in speed that's required at point A for the satellite to achieve the escape velocity and enter parabolic orbit. So it's this out here, so it's passing this right here. So this, the mass, we solved for it, problem 6, I believe. We want to get the mass of the sun. So just brought it over here since we already solved for it in the last problem. And then we could get the velocity, which is the circular velocity, which is here. Also important to note that the escape velocity, in difference that you multiply by 2 right here, which is showed right here, to the GM. All right, and then we know the radius here of A. We just need to figure out this top part right here. So remember this equation for problem 6 when we're trying to find the acceleration of gravity. So we could solve for GM, which is just gravity times the radius squared. So we solve for that here. You know, we have the gravity, the radius times it by 1,000 to convert it to meters squared, and this is what we're given. And then for RA, it's this distance to the center of the Earth, which is the radius of the Earth, which is 6,370. So that's what we did here. 6,370 plus this distance times 1,000 to convert to meters, and this is what we get. So we could now plug that in into the circular and the escape velocities, which are given these two. And it wants us to find the increase in speed. So we minus the velocities we get, so get that. So this given right here. Part B wants us to find the decrease in speed required at point A for the satellite to enter the elliptic orbit of minimum altitude of 6,370. So for this one, we use this equation here that was given to us in the textbook and PowerPoint slides. The reason for that is because we want to solve for h, which h will help us get the velocity at point A. So we'd use this equation for both point A and point B, which I like to call it, which is right here. So I believe it's right there. So we add these together, and we know that data B is equal to data A plus 180, which could simplify to this, which eventually they just cancel out. So we're left with 1 over RA plus 1 over RB is equal to 2 GM over h squared. Then we solve for h, get h by itself, square right here because it was squared, plug in the values, and we're given this for our h. Now we know we could find the velocity by doing h over RA. We know h, we just solved for it, and we know RA, we solved for it earlier in the problem. Plug in the values, and this is what we're given. So now we want to take the difference of this to the circular velocity. So this is what we're given for our final answer, 726 miles per second. And then the last thing it wants us to solve for is the eccentricity. I think I'm saying that right. It's this value right here. So we can find this equation in the textbook or PowerPoint slides. I picked this one. I mean, the solutions use a different way, but I felt this one was easier for me and easier to understand because we know all these values. We know the angle, which is just 180 since it's from one point to another in the horizontal direction. So I'm assuming this y is 180. But yeah, all you really have to do is just get this symbol by itself. That's what I did. Plug in the values, and you're left with 0.334. And these are our final answers for this problem. Now for problem 9, this one's kind of similar to problem 7, that we're given this figure right here, and it wants us to show that the curvature of orbit at each of these 2 points can be expressed as this. So we use the same equation here that we used in the last problem. For both point A, point B, we know that the cosines cancel out for this reason. So we're left with this. And then, I mean, this right here, similar to this right here. So if we were, I talked about it earlier, but I could have done it here. So we could say that, well, I'll just talk about it later. It'll make more sense there. But here we know that velocity equals h over r, and acceleration equals v squared over rho, which is really the radius. So yep, we could plug in the velocity here for acceleration with this, plug that in, and then we have our rho right here, just right here, and it could be simplified to this. And of course we know this from the last few problems we've done, And we also know that it could be equal to this. So you set it equal to each other. You try to get this by itself because that's what we're looking for. So which we did right here. The m's cancel out and also the r squared. And I'm left with this. Now this I was talking about earlier can be solved for here. And that's why I drew an arrow right here to remind me, but you just really just divide 2 to the other side, which you get this. Plug that in into here, and that's our final answer, and that's what it was looking for. So yeah, that's how we got that. And that concludes homework 2, chapter 12.